Hi, I'm Bob. In the last video, we learned that the OLS estimates are unbiased under the zero conditional mean assumption. The unbiasedness of the OLS estimators means that if we randomly sample data from the population many times and run the OLS regressions, the estimates are centered at the population parameter. It is in the sense of sampling distribution when we have many samples from the same population. However, in our research, we usually have only one sample. The OLS estimates of beta 1 and beta 0 could be very close to the population parameter or far away from the population value. So the shape of the distribution of the OLS estimators can help us understand how far the estimate is from the true value. We can use the variance to measure the shape of the distribution. The variance of the OLS estimators is a measure of the spread of the distribution. Since it measures how far the estimates are from the true value for an unbiased estimator, the smaller the variance, the better the estimator. The variance of the OLS estimator is related to the variance of the error term. We assume that the variance of the error term conditional on x is sigma squared. This constant variance of the error term is known as the Homoscedasticity assumption. We don't need this assumption to prove the unbiasedness of the OLS estimators. It's only for simplifying the calculation of variance of the estimators. With the zero conditional mean assumption and the homoscedasticity assumption, we can graph the population model. The zero conditional mean assumption implies that the conditional expectation of y given x is linear in x. It's a straight line. The constant variance assumption suggests that the variance of y given x is constant. So we can graph the population model as follows. The observations are centered around the expectation with variance of the same shape. Let's derive the variance of the OLS slope estimator. We start with the slope estimator's formula. It equals the sample covariance of x and y divided by the sample variance of x. We use the same method we have used many times. That is, to replace yi and y bar with their relationship with x and mu. After some algebra, we get two terms, the population parameter and an expression of x and mu. We further simplify the second term. Next, we take the variance of beta 1 hat conditional on x. The first term is 0 because the population parameter is a constant. For the second term, we take the total sum of squares of x out of the variance sign. We treat it as a constant conditional on x. Remember, when a constant is taken out of the variance gets multiplied by the square of that constant. Then we can switch the variance sign and the summation sign. Inside the summation, it is the variance of a constant xi minus x bar times mu I. Once again, we can take the constant out of the variance. The variance of mu conditional on x is sigma squared by assumption. So the variance of beta 1 hat equals sigma squared divided by the total sum of squares of x. For the variance of the intercept estimator, we have derived its formula in the problem number 10. Please refer to my solution to that problem. Now, let's consider the factors that affect the variance of the OLS estimators. We are interested in the slope estimate because it usually represents the causal effect of the explanatory variable on the outcome variable. For the slope estimate, its variance depends on two things: the error variance sigma squared and the total sum of squares of the explanatory variable x. First, the slope estimate's variance decreases if the variance of the error term becomes smaller. It makes sense because less variation in the unobserved factors in the error term affecting y makes it easier to estimate beta 1 precisely. Second, the variance of the slope estimator beta 1 hat is smaller if our explanatory variable x has larger variation. The more spread out the explanatory variable x, the easier it is to trace the population relationship between y and x. If the explanatory variable has little variation, the estimate becomes imprecise. To an extreme, if x has no variation, that is, all x takes the same value, then it's impossible to do the estimation or run the regression model. Third, the variation of the explanatory variable x usually increases with the sample size. Therefore, a larger sample size results in a smaller variance of the slope estimator beta 1 hat. We should try to collect a big dataset with many observations in an attempt to reduce the variance of the estimates. Next, let me introduce the concept of the standard deviation of the slope estimator beta 1 hat. It is the square root of its variance, that is sigma, divided by square root of the total sum of squares of the explanatory variable x. The size of the standard deviation also depends on the error variance, the deviation of x, and the sample size. Notice that the variance of the error term, sigma squared, is unknown. So it's not feasible to calculate the variance of the OLS estimates using the formula we just learned. However, we can use data to estimate sigma squared. That is, to obtain sigma squared hat. It can be proved that the residual mu hat is an unbiased estimate of the error term mu under the zero conditional mean assumption. We can write the outcome variable in terms of the population relationship with x and the error term. We can also write y in terms of the fitted value and the residual after OLS estimation. Equation 2 minus equation 1 gives the residuals function in terms of population parameters, OLS estimators, explanatory variable, and the error term. This is the relationship between the residual from OLS and the error term. The error term is never observed, while the residuals are computed from the data. They are not the same, but are related to each other. We take the expected value of the residuals conditional on x. Since beta 1 hat and beta 0 hat are unbiased estimator for beta 1 and beta 0 respectively under the zero conditional mean assumption, the OLS residual is an unbiased estimator for the error term. We can obtain the residuals from the OLS regression and use the residuals to compute the sigma squared hat. It is an estimate for sigma squared. Then we can use the standard error sigma hat as an estimate for the standard deviation sigma. So we can use the standard error of beta 1 hat as an estimate of the standard deviation of beta 1 hat. When we look at the formula for standard error of beta 1 hat, we find that it is feasible because we have all the components in hand: the explanatory variable x and the OLS residuals mu hat. In a word, we can compute the standard error of beta 1 hat using x and residuals. Notice that when we compute the estimate for the error variance, that is sigma square hat, the denominator is n-2 because the degree of freedom is n-2. We make a degree of freedom adjustment to obtain an unbiased estimate for the variance of the error term. We can get the standard error of the Intercept estimator using the same method. All the econometrics and statistics software reports the standard errors of the beta 1 hat and beta 0 hat. Here's an example in Stata. We use the dataset containing adult children's labor income and their parents' average annual income during childhood. You can download the dataset from the link below. When I regress children's earnings on their parents' income, I obtain the estimated coefficients and their standard errors. The standard errors are computed using the formula we just learned. To verify it, we can obtain the OLS residuals by typing the command predict res, residual. Then we generate the residual squared by typing generate rig squared equals rig to the power 2. Now we have the squares of the residuals. We sum them up. To do that, we can use the command summarize. This command returns the sum of values of all observations and the number of observations, the sample size. We use a scalar to store the value of the sigma squared hat. The sigma squared hat is computed according to the formula we just learned. We can take a look at the value. Then we calculate the sigma hat. The next step is to compute the square root of the total sum of squares of x. Here x is the log of parents' income. Based on the formula, we need the sample mean of x. We can type egen x bar equals mean followed by x inside the parentheses. Then we compute the square root of the total sum of squares of x. Finally, we can compute the standard error of beta 1 hat by sigma hat divided by the square root of the total sum of squares of x. It is 0.020381. It turns out that it is exactly the same as the OLS regression reports. The OLS estimators, variance, or standard deviation is not feasible, so we use the standard error to estimate it. The standard error of beta hat gives us an idea of how precise the estimator is. We use it to compute the t-statistics and confidence intervals. We will discuss it later. Thank you for watching this video and subscribing to my YouTube channel. See you next time.